Today we're going to talk about Gibbs energy and where that free part comes in. Why do they even call it Gibbs free energy? And I think some of it makes sense to us. Reactions, sometimes they happen and sometimes they don't. But all the ones that are really familiar to us that just happen are exothermic. They produce heat. For example, think about this. If I light a log on fire in my fireplace, it's going to burn. We know it's going to burn. It's going to happen. And so we call it spontaneous. I think some people get a little confused about that because they say, well, I have to light it on fire. It's not just going to all of a sudden happen by itself. But that's not really the definition of spontaneity from a chemical perspective. So let's break it down. Let's just jump right in. If I write the equation for Gibbs energy is equal to the change in enthalpy minus temperature times the change in entropy. And what we want to do is not math here. We want to make this make sense. And so how we're going to do that is we're going to talk about each term individually, starting with enthalpy. Enthalpy is heat. We hear that said a lot, but what does it really mean? I'm going to draw a vertical axis, and here on this vertical axis is going to be energy, but not just any energy, chemical energy. And I'm going to stick with the log example because it's something we know. If I have a log and oxygen, we know there's chemical energy in it because we burn it, it makes heat. Like there's chemical energy in gasoline because if there wasn't, how could it move your car? Anything that makes heat, that heat energy comes from somewhere. And when you burn a log by mixing it with oxygen and adding some heat to get it started, it produces heat. So if I add a little heat to this, put a spark into it, and then it will burn. And eventually, it's going to make ashes and carbon dioxide and water. We know this. It's fire. Those are the products of fire, in this case, with a log. And, of course, it's going to make heat. And hopefully all of that makes sense. Energy cannot be created or destroyed. We started with a lot of chemical energy. There's clearly very little chemical energy left in ashes, carbon dioxide, and water. Where did the energy go? It went into heat. And of course, this reaction is spontaneous. And I like to think of it like this. If I had a big rock at the top of the mountain and I pushed it, I have to give it a little push over. After I push it over, it is going to fall to the bottom. And when it falls to the bottom, it's going to release a lot of energy. As we would see, as you can imagine a rock falling off a mountain being quite destructive. For a long time, this was the understanding of chemical energy. Yet, there's this missing piece. Because sometimes some reactions happen and they get colder. And I'll give you a common one. If table salt dissolves in water, it gets slightly colder. And that became difficult for people to explain until the discovery of entropy. Entropy is an interesting concept. I like to think of entropy as disorder. Things like to be disordered. In fact, if I just dump a pile of sand on the ground in the middle of your classroom in the morning, and we wait till the evening, the sand is going to be everywhere. Just statistically, each piece of sand moves a little bit each time it's bumped, and the probability of all the sand coming back to the same place is very, very small. So the sand is going to spread out. It's going to tend towards disorder. If I put a drop of food coloring into water, it will spread out over time. And no matter how long I wait, that food coloring will never come back to be a drop of food coloring in clear water. Why? because the food coloring is actually just a ton of tiny little molecules, and the water molecules are all moving around, and they bump into each other, and they take a randomized direction every time they move, and eventually they end up distributed statistically, which means an even distribution in the water solution. That should make sense to us. The Earth tends to disorder. But now let's imagine a situation. Let's say there's a little bit of a barrier. Like instead of dumping sand just in the middle of your classroom, let's say your classroom floor is sloped a little. So the sand wants to fall down, but people are moving it around. And so it starts going out, but it kind of wants to come down. Will the sand still spread out? And of course it will, right? If there's just a little bit. But if there's too much of a slope and there's a pit, the sand will stay down in the pit. And this is the type of energy argument we get in with entropy versus enthalpy. If you put a rock on the top of the mountain, of course it's going to fall to the bottom. But in some situations, if the rock is light enough and the slope isn't too steep, the little tiny rocks with some effort from randomized energy might move up the mountain. And of course, that's a classical analogy to a chemical example, but the idea works. So let's break this down, how it is possible that table salt dissolving in water gets colder. We're putting table salt into a beaker of water. And if you've ever looked closely at table salt is many, many perfectly beautiful little square crystals. And if you haven't ever really taken your time to look closely at table salt, I suggest you do it. It's quite a fascinating discovery to realize that table salt is a ton of perfect crystals. Maybe not perfect, but crystals nonetheless. Crystals are highly organized. From an entropy perspective, that's not desirable. Remember, the universe tends to disorder. So crystals are highly ordered. So the universe would tend to destroy those. Also, the sodium chloride is all in one place. Disordered would be if it was spread evenly everywhere. So when this salt dissolves and it becomes a beaker of transparent water, but we know the salt ions are spread out evenly in solution, this is more disorder. And so we can think of it, if we have a scale this time and the vertical axis is disorder, as we go up this, we're going to more disorder. So here are our crystals of salt. And up at the top, in more disorder, is our dissolved salt. Entropy is a state function. And so that we know the total entropy is going to equal the entropy of the products minus the entropy of the reactants. The entropy of the products minus the entropy of the reactants. So here, products are big and the reactants are small. So delta S is greater than 0. And so entropy is the opposite of enthalpy. In things that are spontaneous, the entropy tends to be greater than 0. If the spontaneity of the reaction is caused by entropy, it's greater than 0. Think about the food coloring spreading out in the water. That's a spontaneous event. You don't have to do anything. You put the food coloring in, it spreads out. I would say that's a 0 enthalpy reaction. If you put a drop of food coloring in water and let it spread out, it's not going to get hotter or colder. The temperature's not going to change. It's driven by the fact that the change in entropy is greater than 0. Now remember, we said salt dissolving in water is endothermic. That means if we go back and we look on the energy scale, remember this is chemical energy, that means that the products, dissolved salt, has more chemical energy than the crystalline salt. This is strange from an enthalpic perspective. This would be like all of a sudden the rock flying to the top of the mountain. It confused chemists for a long time. How can a rock just all of a sudden spontaneously fly to the top of the mountain? Well, this is where entropy comes in. The rock flies to the top of the mountain because when it does so, it becomes so much more disordered. The salt wants to spread out in the water so badly. The crystals are too perfect. They have to be destroyed. And so there's the entropy will drive it up this mountain. And again, if we go back and we look at the equation for Gibbs energy, the change in Gibbs energy is equal to the change in enthalpy minus temperature times the change in entropy. And we've already said that if delta H is negative, that is exothermic, and that's spontaneous. That means that delta G, if it's negative, it's spontaneous. We can keep that in our heads because without any contribution from entropy, a log burns. So we know delta G is spontaneous when it's negative. Now, delta H in this case of the salt dissolving in water is positive. Remember, products minus reactants. Something bigger minus something smaller is positive. So that means that this term has to be negative, which means the change in entropy has to be greater than 0. And of course, here in the salt dissolving, we already explained that the entropy is greater than 0 because the crystals start off all nice and neat in one place and all pretty, and they end up dissolved and spread out and not beautiful at all. And so they've tended towards disorder. Delta S is greater than 0. The temperature term also comes into play here. And if you understand Le Chatelier's principle, this helps here because this crystalline water solution needs to take in heat to go uphill and become a dissolved salt. It has to take in heat. That means heat is part of the reactants. That means if I add heat to the reactants, I drive it towards the products. And so adding more heat drives this reaction to products, but it also makes this term bigger. Of course, temperature is always a positive term. If delta S is positive, this term gets bigger. And really, what we need for Gibbs energy to be negative when delta H is positive is for this term to dominate and become so negative that it erases the fact that this crystal has to go uphill in energy to become a dissolved salt. And that's really why we call it Gibbs free energy. We know if it's exothermic, it tends to be spontaneous. But If it's endothermic and this term dominates with a large delta S and a high enough temperature, then it can be spontaneous even when it's endothermic. So it's not just the energy of the reaction. It's the energy of the reaction combined with the entropic factor. And so that drives the spontaneity. So Gibbs free energy, it's the energy that's free after you account for the entropic effects. And that can take from or give to the value of delta G. And it's a little bit of a strange thing. I never liked that they called it free energy. I always thought that somehow that meant I could heat my house without paying any bills. But that never turned out true. It turns out that it's just the energy that's left over to drive the reaction after the entropic effect. So the energy that's free to drive the reaction is Gibbs free energy. And so I hope that's helpful just from a conceptual perspective. And now, if you understand that part, when you get into the mathematical parts, you're less likely to make sign errors. You know, when I teach chemistry, I always say, if you're wondering which sign it is and you're trying to remember, is this positive or is this negative here, back up. It means you're lacking a conceptual understanding of what you're doing. You should be able to determine the sign and the significance of any sign from conceptual reasoning. Thank you.